Welcome to this explainer. Okay, today we're diving straight into the hidden role of variance in our predictive models. We're going to track down the mathematical culprits that are silently corrupting our data. If you've ever built a statistical model and thought, why on earth are my predictions getting so wild at the extremes? Well, you're in exactly the right place. Let's put this into perspective with two real-world scenarios. Imagine tracking a family's food budget as their income grows. At lower incomes, spending is tight, super predictable. But as wealth increases, the choices absolutely explode. Some billionaires are eating cheap fast food, while others are dining on caviar every night. The variance just goes off the charts. Now flip that and think about an expert typist. When you first start learning, your error rate is all over the place. But after hundreds of hours of practice, those errors stay consistently low, regardless of whether you practice for 1 extra hour or 10. That variance is totally locked in. So these everyday examples perfectly highlight two terrifyingly long words in statistics. First, homoscedasticity, which just means the variances are locked in and disturbances are pairwise uncorrelated. And then there's heteroscedasticity. This happens when the disturbances in your model have variances that are absolutely not constant across observations, kind of like those chaotic food budgets we just talked about. Visually, the difference is night and day. Notice how the homoscedastic scatter stays perfectly contained within a neat, parallel band as we move along the x-axis. The spread of those distribution curves is identical. But then, look at the other side. As our explanatory variable changes, the variance expands wildly. It literally fans out. That right there is exactly what increasing variance looks like in a linear regression model. Section 1, Causes of Heteroscedasticity, Profiling the Culprits. Now that we know what this anomaly actually looks like, let's figure out what causes it to infect our models in the first place. You know, what's really interesting is just how mundane the causes can be. According to econometric data from IIT Kanpur, the main suspects range pretty widely. Sometimes it's just the nature of the beast, like those consumption trends. But often, it's actually how we handle the data. For instance, if you use average data, like recording clothing expenditure for a whole family instead of per individual, the math naturally introduces variance based on family size. Other culprits? A skewness in your explanatory variables, or even just applying the wrong mathematical transformation to your model. Section 2, the agitation why unequal variance matters. Let's get into why this actually ruins our statistical models. Here is the absolutely crucial point. If you run a standard ordinary least squares regression on heteroscedastic data, your estimators actually stay unbiased. They'll still hit the target on average. But, and this is a big but, they completely lose their efficiency. The covariance matrix shifts, meaning your standard errors become incredibly unreliable. You might think a variable is totally insignificant when it actually is, or vice versa. Long story short, using OLS when your variance is chaotic means you're literally using the wrong tool for the job. Section 3. Testing for heteroscedasticity, the interrogation. To restore trust in our models, we have to put on our detective hats. Let's look at the lineup of tests. First up in the interrogation room is Bartlett's test. Formulated way back in 1937 by Maurice Stevenson Bartlett, this one is fantastic for checking if multiple samples share the exact same variance. It builds a null hypothesis of perfect homoscedasticity. But there's a huge catch here. To use Bartlett's test, you absolutely must have replicated data for every single observation. Sure, that's common in controlled experimental sciences, but in real-world economics, incredibly rare. Plus, there's a famous philosophical issue with how this test is used. Back in 1953, statistician George Box joked that using Bartlett's test just to check if you're allowed to run an ANOVA is profoundly silly. He actually compared it to risking a tiny rowboat at sea just to check if the weather is calm enough for a massive ocean liner. Why? Because the ANOVA F-test is pretty robust to different variances, while Bartlett's test is extremely sensitive to even the slightest departure from a normal distribution. So, what do we do when we don't have that nicely replicated experimental data? Well, we deploy the Bruch-Pagan test. This is an incredibly powerful, widely used tool that checks if our variance is being corrupted by one or more of our explanatory variables. You basically run your standard regression, take the residuals, square them, and then run a second regression just to see if your variables can predict those squared errors. If they can, boom, you've caught heteroscedasticity red-handed. Section 4, the Goldfeld Quandt approach. If you suspect one specific variable is causing your variance to blow up, this is one of the most reliable forensic tools you can use. This test has such a rich, evolving history in econometrics. It was introduced in 1965 by Stephen Goldfeld and Richard Quandt specifically to tackle economic models where variance increased right alongside things like income levels. Then, by 1969, Herbert Glaser validated its incredible small sample power using Monte Carlo simulations. Later on, in 1982, Jerry Thursby analyzed its sensitivity, warning everyone that if you misspecify your model, say by forgetting a key variable, the Goldfeld Quandt test might actually trigger a false alarm. The mechanics here are just ingenious. First, you take your suspect variable and rank all your observations in decreasing order. Next, and this is the brilliant part, you split the data in two, completely throwing out a chunk of C observations right in the middle. By dropping that muddy middle section, you create maximum contrast between the high variance end and the low variance end. Finally, you run separate OLS regressions on those two distinct parts, calculate their residual sum of squares, and compare them using an F statistic. Section 5. Fixing the data, the resolution. Okay, so what's the remedy once we've definitively proven that our data is guilty of heteroscedasticity? This is where we apply a technique called generalized least squares, or GLSE. Instead of just throwing our hands up and abandoning the data, we perform a mathematical intervention. We literally deflate the model. If we know the exact nature of the varying variance, we can mathematically divide our variables by the specified standard deviation. This brilliant little trick smooths everything out, restoring order, homoscedasticity, and most importantly, statistical efficiency to our data. By applying this transformation formula to divide our variables by the standard deviation, we effectively neutralize that varying variance. But hey, a quick word of caution from the experts at IIT Kanpur. When you divide your entire equation by a variable, the roles of your intercept and your slope parameter can actually swap in the newly deflated model. So it's a highly effective fix for sure, but you really have to read your software output carefully. Otherwise, your conclusions will be completely upside down. We've seen today how variance isn't just random noise. It often tells a hidden story about the very nature of your subject, whether that's income, behavior, or the limits of human practice. So I'll leave you with this provocative thought to ponder. If your model's variance is hiding a powerful trend, what other secrets is your data keeping from you? Keep questioning your residuals and keep exploring.